Yes, let's continue with this example. Any other questions you have? Batteries are? Similar. If V1 is equal to V2. Well, I don't have the exact solution yet, so I cannot really say what happens in that case. But at least in these limits that we had discussed, in these limits, if R1 is infinitely large, R1 resistance, and if V1 and V2 have the same strength, then there won't be any current running through the system. Because just this V2 will be pushing the current in one direction, V1 will be pushing it in the opposite direction. If they have the same strength, they will not be able to create a current. But in this case, if R2 is infinitely large, this resistance is infinitely large, there is no current running through it. It is as if this wire doesn't exist. It is just like an insulator over here. So V2 has no effect whatsoever on the current running through the system. Okay, so if you change the polarity of V2 or you change the sign of V2, but as long as R2 is infinite, this battery is as good as it doesn't exist. Because this infinite resistance just will separate it from the rest of the circuit. Now, in the first case, if you change the polarity of this battery, both of them will be trying to run the current in the same direction, so that will be the direction of the current. Okay. Okay, so your friend has this question. If you know that the network cables, for example, that connect the continents, like the Europe to the Americas, I mean, they are hundreds of kilometers long. So that means they have a huge resistance, since the length is large. But you see, they are also very thick. That will drop the resistance. Okay, so on one hand, the resistance is increasing. On the other hand, the resistance is dropping. Furthermore, still the signal strength gets weakened. So what they do is they put some repeaters. They enhance the signal midway. So there are such effects. But let's stick with these circuits. Okay, now, no matter how complicated your circuit is, so we started with two different examples. For example, we had this circuit, and we had these three unknown currents. We could write down three equations. Now, in this one, we would have 1, 2, 3, 4, 5, 6 currents, 6 unknown currents in this example. You can just choose them to be, again, this one, let's call it I1, I2, I3, I4, I5, I6. You have 6 currents, 6 unknowns. You have to write 6 equations. And using exactly the same principles, you can write down 6 equations. What you need to do is just pick some arbitrary point you like, of your choice. Start from that point, go around your circuit in different ways that you can come up with. So that will give you some number of equations. For example, in this case, I can start here, go along this lower path. That is one equation. I can start here, go around the upper path. That is my second equation. Or I can start from this one, go from the lower path, go to the above path, and then down. That will give me my third equation. This one. Okay. I3 is this one. Okay, if I2 is 0, then I1 is equal to I3. But I had, okay, so let me first finish the equations we have, then we can discuss. Now, I have all these three equations just by starting from here, going around an arbitrary path back to the same point. The potential difference between a point and itself should always be 0, independent of how you calculate it. Now, then I still need to have three more equations, at least three more equations. I can use the conservation of charge. There cannot be any accumulation of charges anywhere. So all the currents, that the sum of the currents carrying a charge to an arbitrary point should be equal to the sum of the currents that are taking charges away from that point. If you look at this point over here, it is kind of trivial. It is I1 taking charge at this point, and so it should be I1 taking charge away from that point. It is trivially satisfied. But if you look at this point, for example, this point over here, it will tell me that I1, this is the currents that are carrying charge into my point. This should be equal to I2 plus I3. This is one more equation I have, so that makes 4 equations. Here I have another equation, which is the charges taking current into that point is I5 plus I6. And the current that is taking charges away from that point is I1. That made me. The 6 is this one, I6. So this I have I6, here I have I5, here this is I1. And then I still need one more. I can just look at, let's say, this point over here. The currents that are taking charges into that point is I3. The currents that are taking charges out of that point is I4 plus I6. So that gives me, I had 3 equations for considering 3 different ways that I can go around this circuit and come back to the same point. And now I have 3 more equations just using the conservation of electric charge. That gives me 6 equations for 6 unknowns, which it might take long, but in principle you can solve them. Now, just one more thing about this circuit. So if you look at this example, now we said that, let's say, in this limit, if R1 is infinitely large and if V2 is larger than V1, so we said that I3 will be positive. So this battery, in time, it will lose its charge. It will just become an empty battery. I1 is negative, so we are dumping charge on this I1. Well, that is, we are trying at least to charge this battery. Now, the battery just works by ordinary batteries, let's say. They just work by some chemical reactions. Non-rechargeable batteries, though in non-rechargeable batteries, those chemical reactions will not be, you will not be able to reverse them. So if you try to charge non-rechargeable batteries, you will be mainly creating some other chemicals, and it will no longer function as a battery. In rechargeable batteries, the chemical reactions that are creating the charge, they can be reversed. So since they are reversed, if you are taking charge away from the battery, there will be chemical reactions creating the current, and hence you are using kind of your fuel. Once the chemicals are finished, you cannot create any more current. But if you reverse the current, rather than taking current from the positive terminal, you give current to the positive terminal. In that case, you will be reversing the chemical reactions, and hence you are converting electric energy into chemical energy, which are stored in your rechargeable batteries. Questions? You bite them. How many of you bit some batteries? Yes. Okay. Why? I also did that. Okay, you see, the chemical reactions, the potential difference that you create depends on the concentration of the chemicals. When you are biting them, you are reducing the volume and increasing the concentration of your chemicals. And hence you can get some more charge from the battery. Okay, the chemical reactions, you cannot stop them. They keep going. And although air itself is not such a great conductor, nevertheless it is a conductor. There is some humidity. So if you want to save your if you are not using your batteries, and you will find out that after, let's say, after some time, nevertheless your battery is over. I mean, it doesn't have any power left. But if you put it in a refrigerator, you are slowing the chemical reactions, so they will last longer. I4 is equal to I1, not necessarily. No, it's not a Wheatstone bridge. No. Why should it be? It doesn't have to be. What do you mean expanded? Okay. No, you cannot. Not this one. No, not this one. I mean, there is a special condition under these resistances. I think it was if the ratio of R2 to R1 is equal to R4 to R5, in that case there is no current running through this one, so these 2 points have the same potential. Then you can just connect them. But in the general case, it doesn't hold. Try it. It will be fun. So what will happen to that electricity? It will. Okay, any other questions on this one? I don't know, I have no idea. You cannot without actually solving the problem. And you don't need to. I'm just saying that I will assume that I4 is positive if it is moving in that direction. That is the only thing I'm saying. At the end of my calculations, I4 can turn out to be a negative number. But I will only just interpret it as meaning that the current across this resistor is not going upward, but it's going downward. I don't need to know the direction of the current. I just choose some positive direction, some positive sense of the current. Other questions? Now let us also add the capacitors to our circuit. Now let's start with a simple example. We have some electromotive force over here. Let's add some resistance over here. And let's add a capacitor over there. If we wait long enough, what will be the current in our circuit? So what will happen in this circuit? So I have this discharge capacitor. I connect it to my circuit. So there will be a current running through my circuit. And I will have my capacitance. My capacitor will be charged. It will keep accumulating the current charge until it is fully charged, which means, in this case at least, until its charge reaches, if Q is equal to C times epsilon. If Q is equal to C times epsilon, this just means that the potential difference between these 2 points and the potential difference between these 2 points are the same. They are equal. So the potential difference across the resistor is 0. But that means the resistor, there is no current running through the resistor. So when this is reached, there won't be any current running in my system. This is Q max. This will be reached eventually. And at this time, the current running through my system will be 0. Now, what happens at the instant that I connect my capacitor? Something large. Large. We will see that it will be infinity. Which one? Well, I mean, we are not specifying what is long. I mean, for some people, 10 years is short. For some people, 1 second is long. So, I mean, this just means that it is long compared to whichever scale you take. Well, there is always some resistance, no matter how small. Now, at time t equal to 0, well, at least if let's say after 5 minutes the current is 0, when the time is infinity, it is still 0. Now, at t equal to 0, Q is equal to 0. So what is the current running through my system at this instant? Why? I just at the instant that I connect my capacitor, there hasn't been enough time for any charge to accumulate on my capacitor yet. So the potential difference across the capacitor is 0 in this case, since there is no charge or negligible charge. So the potential difference between these 2 points of the resistor will be just epsilon, which means that the current in my system, I is equal to epsilon over R. Okay, so these are 2 limits that we have, which tell me that if the capacitor is fully charged, it just behaves as if it is an open circuit. There is no current running through it. If the capacitor is completely empty, it behaves as if it's a short circuit. So these are 2 limits that we have. And eventually our result should show these 2 limits. Now let's calculate what is the current at some arbitrary time. And how does the current goes from epsilon over R to 0? And how long does it take? I mean, in that case, we will be able to say what is large T. At the time being, I don't know what large T means. I only know that for sufficiently long time, whatever that means, the current will go to 0 after sufficiently long time. Again, Kirchhoffs, we will use the previous laws that we wrote over here are what are called the Kirchhoffs Rules. They are mainly the independence of the potential difference, the independence of the potential difference on the path that you use to calculate the potential difference, and it's the statement about the conservation of electric charge. Now we have this circuit. Now, what is the positive plate of the capacitor? The left one. So at this instant, I will say that the charge is Q of t. I don't care. It is just a convention. I will say that Q is positive if this plate is negatively charged and the other plate is positively charged. I will say Q is positive. No, Q is positive if this plate is negatively charged, this plate is positively charged. Q is negative if this plate is positively charged and this plate is negatively charged. It's just a definition, just a convention. No. Well, let's choose the positive direction of the current also. The charge of the capacitor. Well, you see, which Q is this over here? Because basically this is what we will be using. This Q is the charge in any one of the capacitor plates. This V is the potential difference. Now, in this equation, we didn't care about whether the potential difference was positive or negative. We didn't say the potential difference between plate A or plate B. We just said the potential difference. We didn't care. Now we need to pay a bit more attention. So I first have to define what I mean by a charge, what I mean by a positive charge or a negative charge. I have to define what I mean by a positive potential or a negative potential. So now I'm just defining those things. I'm defining the positive and negative directions. That's the only thing I'm doing. You can choose whichever direction you like. I just preferred, just to confuse you a bit more, I just prefer these directions. Well, let's see. If Q is positive, well, we will write down the Kirchhoffs rule in a moment. And so these directions are arbitrary. Choose whichever one you like. I mean, of course, in the exam, you will not be choosing these directions. But since I'm just trying to confuse you, I will be sticking with these directions. And it will just turn out, I know, you can also tell me that eventually I will turn out to be negative, Q will turn out to be negative. But so what? The important thing is how you interpret your results. So now let's write the Kirchhoffs rules. Well, there's no splitting up of the wires, there's only one loop. So let's start from this point and go around like this. So this is A, B, let's say C, and D. So the potential drop as I go from A to A is VAB plus VBC plus VCD plus VAD. Now, what is AB? Potential drop. VAB, BC, CD, DA. That makes a difference. I'm going around the continuous loop. Now, what is AB? The potential drop as I go from A to B. Potential drop is IR or minus IR. I'm writing a potential drop. Or let's write the potential increase as I go from A to A. This is not potential drop, this is the potential increase. I mean, you see the current is running from B to A. So the point B has a higher potential than point A. So IR is the potential increase as I go from A to B. I'm writing the potential increases this time. Why? Well, the total potential increase should also be 0. I'm at the same potential. If I sum always the decreases in the potential, the sum should be 0. If I write all the increases in the potential, the sum should be again 0. Or let's say minus. Drops again. The potential drop is minus IR. Now, what is the potential drop as I go from B to C? Minus or plus? Potential drop. No, I don't care. You see, the potential difference across a resistor doesn't depend, across a capacitor doesn't depend on the current. It only depends on the charge in the capacitor and its capacitance. So it should be Q over C. We are writing the potential drop. You see, Q is positive. If this is positively charged, this is negatively charged. So if Q is positive, as I go from B to C, I'm going to a higher potential. So the potential drop is negative. So if Q is positive, the potential drop has to be minus Q over C. Well, there is no charge accumulation anywhere, except on the plates. The plates are accumulating charges, but there's no charge accumulation, let's say, in the battery. The battery will remain neutral. So whatever current is leaving the battery, the same current should enter the battery. Yes. I'm just looking at my system at some arbitrary time t. Not t equal to 0, not t equal to infinity. Okay, now I'm at the point C. What is the potential drop as I go from C to D?
Minus 0.
Yes, minus 0. What is the potential drop as we go from D to A? Oh, well, okay, the EMF of this battery is E epsilon, or let's say V. That's minus V. The potential drop. The potential is increasing, and increase in the potential, you can also say a minus negative decrease in the potential. Okay, now, this is one equation. Of course, here the difficulty is I have two unknowns, Q and I. I have to find a relation between the two. Now, let's suppose that the current I runs for a duration dt. Okay, how much charge does it put in my capacitor? I times dt, because remember what we define as the current is the charge passing through a point in a unit time. So if the time is dt, I times dt is the change in the capacitance, in the charge on the battery. And if I is positive, dq is also positive. No, this is the derivative. So this tells me that the current and the charge in the capacitor are related by I is nothing but the derivative of the charge on the capacitor plus. Of course, now we have to take this, put it over there. So we have the charge on the capacitor satisfies this equation. Now minus dq by dt minus q over c. This should be equal to, no, minus v. This is r minus v. This should be equal to 0. So Q should be such a function that if you take its derivative, multiply with R minus R, subtract the Q over C, and then subtract V, you should get 0. We should find such a function. Okay, any questions until we write this equation? Well, of course, this minus V, I can just move it to the other side, and it will be, this term should be equal to V. Well, just in all of these Q's, Q is a function of time. Right? I mean, I don't want to just put too much things in the equation. The Q is a function of time in all of these. Okay, so let's try to simplify it a bit. dq over dt plus q over rc should be equal to v over r. Okay, this is the same equation. So what is the solution? I mean, you will learn how to solve these equations. Now it will be just trial and error, try and error. I mean, I can tell you that the solution of this equation is just a e to the power minus t over rc plus v over c. Now v times c. Now if you just take this equation, take this expression, put it over here, you will see that it does satisfy this differential equation. Which one? These ones? Well, I just move these to the left. This is a minus. Now we were also given one more information. At t equal to 0, there is no charge. This is Q of t. Q at t is equal to 0. This is A minus Vc. This should be equal to 0. This is our initial condition. So A is equal to Vc, so the charge at an arbitrary time is equal to V times C minus V times C1 minus e to the power minus t over Rc. Some arbitrary coefficient. I mean, if you remember your mechanics courses, I mean, there, for example, we had, okay, if you know the acceleration of your object, the position at any point, at any time, depends on the initial velocity and the initial coordinate of your object. So those were the two unknowns, and they are not determined by the dynamics. They have to be given for the chosen system. Now, in this case, we have a similar thing. We have an equation, and any such function is a solution of this equation for any value of a. Whatever the value of a, this function satisfies this equation. How do we determine a? By the initial conditions. We were given that at t equal to 0, there is no charge. Which one? This one. You will learn next year. I mean, at least for such a differential equation, they are easy to solve. There are various tricks to solve this equation, which, as I said, you will learn next year. For the time being, it's just a trial and error. given this function, if you put it over here, you will see that it does satisfy our equation. Inside my capacitor in this circuit. Okay, so your friend is saying that, okay, we have this charge in the capacitor which is connected to a battery. After some time, it should become a constant. So let's say t becomes very large. So what is the property of this exponential function? I mean, you see, if you remember the graph of this exponential function, e to the negative a large number, is negligible. It is just 0. It just decays. So this is 0. What remains is just a constant. And if you would plot Q as a function of time, this is our Q. If you would plot it, okay, at t equal to 0, e to the power, any number raised to the power 0 is just 1. 1 minus 1 is just 0. So at t equal to 0, we start with 0. When t is very large, this exponential just becomes 0. So what we are left with is minus Vc. So this is how Q would change as a function of time. So in fact, in the beginning we said, okay, t goes to infinity. This mainly means, in this case, if you look at this expression, time always appears as t over Rc. So this just means t is much larger than Rc. This Rc just means the time constant. Now, for example, if you would if you want to measure the capacitance, now this week you are doing an experiment where you have a device that measures the capacitance. Now you can determine the capacitance of an object by just looking at this graph. So how fast does it decay? How fast is it as a battery charge? It depends on two things, your resistance and the capacitance. If you know the resistance and if you look at this shape, you can determine the capacitance. Now this is number e, the natural logarithm, the base of the natural logarithm. The logarithm of e is just 1. E is something like 2.7, etc. Now let's write down the current also. This is the charge in the capacitance. Now we also know that the current is nothing but dq by dt. This is d by dt of minus Vc times 1 minus e to the power minus t over Rc. If you take the derivative, minus Vc is just a constant. Here you have 1 over Rc times e to the power minus t over Rc. Okay, the c's cancel, so it's minus v over r, e to the power minus t over Rc. This is the current, of course, as a function of time. Now again, if you would plot this, this is I and t. Now at t is equal to 0, this exponential is just 1. So the current is nothing but minus v over r. Now we will discuss what that minus is in a moment. So at t equal to 0, we start with minus v over r. When t becomes very large, that is much larger than Rc, it will go to 0. So this is the current. Now, two things you should notice. The current is always negative. And the charge is always negative. Both of them are always negative. Now, what that negative means is basically that for this circuit, This plate will be charged positively and the other plate will be charged negatively in the actual case. That is what the negative Q means, because we started by defining a positive Q. The capacitor has a positive charge when the plate on the right is positively charged and the plate on the left is negatively charged. That is how we define the positive charge of the capacitor. Now, our calculations just told us that the charge of the capacitor is negative. It just means that this left-hand plate is actually positively charged and the right-hand plate is actually negatively charged in the actual setup. And we have also found that I was negative. The current running in this circuit is negative, which mainly tells us that the current will not be moving in that direction. The current will be running in the opposite direction, as you had already guessed. Okay, first of all, electron is very slow. It's just 0.05 meters per second, more or less, or 0.5 millimeters per second. That is the speed of the electron. Now, this speed over here is the speed at which the capacitor is being filled. No? Why? You see, the charges are moving very slowly on the average. Not necessarily. You see, this V is any EMF source. I mean, so what is actually happening over here is there are two things. One is the capacitance is affecting. So as the battery is being charged, it will lower the current. Because as the battery is being charged, it is building a potential difference that is opposing the potential difference created by the battery. So just imagine it like this. There is a group of people. You are pushing that group of people to one direction, whereas somebody else on the other direction is complaining, then he is pushing back. So in the beginning, he will not push back. The capacitor will not resist being charged. So the charges will easily go and they will start accumulating in the capacitor. But with time, as more charges are accumulated on the capacitor, it will resist, so the charging slows down. So that's why we have this decay. So initially, the capacitor doesn't react, but then as the capacitor is being filled, it will react. It will resist being charged more. So the current will slow down. Furthermore, there is the resistance. The resistance itself will resist any current. It will just slow down any current. If you want to lose, okay. Now, what do you mean by the age of the capacitor? Consumed, what do you mean by consumed? Well, we already have the solution for that. Your friend is asking this question. Suppose we have this system and we wait long enough so that the capacitor is fully charged. Now, what happens when we change the terminals of the capacitor? We just take it off and connect it the other way around. So that would basically mean let's say another example. Again, we have the same system. And let's choose the positive directions as we did before, minus plus. But you are saying that initially, Q at t equal to 0 is nothing but V times C. So this is your initial condition. Now we already know the solution. This is our general solution already. So you need to determine the value of A for your initial condition. This A, and you know how it changes with time. But whatever the value of A is, the decay is always determined by R times C. Okay, the total time that it takes for the capacitor to be fully charged is infinity anyway. And we can discuss it later on, but I mean, conceptually, is there any questions? Rather than specific problems. I mean, we need to leave. We will be continue discussing on Tuesday. No question? Okay, we will continue on Tuesday. You will have a pre-report. You will have a new homework. Don't forget that.